Hello, everyone. Welcome to our talk, and it's very nice to see all of you here. So in today's talk, we are going to present you our LLM4Shell, discovering and exploiting RCE vulnerabilities in real-world LLM-integrated frameworks and applications. As you can see, we have two speakers here. First, I will introduce Tong to introduce himself.
Hello, everyone. My name is Tong Liu, and I'm the first-year PhD student from University of Chinese Academic and Sciences. And my research interests mainly focus on AI plus security, which mainly focus something AI security and how we can use AI to assist security techniques like fuzzing. And in my spare time, I'm a CTF player at Now and Trailhead. And that's my introduction of myself.
And as Tong said, he's a first-year PhD student, and I'm actually a first-year lecturer. I'm currently a lecturer at University of New South Wales, and my research interest mainly lies in software testing and software security analysis, especially fuzz testing. And we have three contributors for this work, and all of them are from University of Chinese Academy of Science. And here is today's outline. So first, I will introduce you the background and a motivating example of our study. And Tong will show you the technical details of the detection of this vulnerability, the exploitation of this vulnerability, and how to mitigate this type of vulnerability. So first, let's come to the introduction and background. So here we need to be clear about what is the subject we have studied here. So as you can see, the subject is a system made up of LLM-integrated frameworks and LLM-integrated applications. Actually, like web applications, most of the LLM-integrated applications nowadays are based on certain frameworks. And we are not studying arbitrary applications and frameworks. We are studying the frameworks that has the capability of generating and executing some code. So you may wonder, why do we need some applications to be able to ask large language models to help us to generate code and execute code? So you may wonder, why do we need this feature? Actually, the answer is because large language models themselves sometimes cannot answer certain questions from the user. For example, we all know that large language models are not good at solving mathematical problems. But instead of answering the mathematical problem directly, they can generate a program and execute that program to get us the mathematical problem answer. So that's why, in certain cases, we need to allow large language models to generate some code and use the code execution result as an augmentation for the final answer. So that's why we need this. And this is the subject of our study. And here's a typical workflow of this system. So first, the user asks a question that would require code execution. And then this question is passed to the relevant API of the framework. And then the framework will ask the large language model to generate some code to solve the problem. And then the large language model will generate the code. And this code is handled and executed by the framework. And the execution result is passed back to the application. And the application will combine everything together and present the final answer to the user. So this is the system of what we are interested in. So the question here is this system really safe? So in order to understand the safety of this framework or of this system, we need to know what are the existing attacks against large language models. Actually, there are three main types of attacks which are all related to prompt engineering. The first type of attack is called jailbreak. Actually, large language models, when they are trained, they need to go through, before they are released to the public, they need to go through some safety training to avoid this language model from generating harmful content. For example, if a user asks, how should I build a bomb? The large language model should answer, no, I can't help you with that. But some malicious users can craft a prompt so that to allow the large language models to answer some forbidden questions. And that is called jailbreak. The second type of attack is called prompt leaking. It's also related to prompt engineering. So in some applications, there are system prompts which serves as the context of the user-provided question. And in some applications, this system prompt could contain sensitive information, such as some copyright, such as some information protected by copyright, or some user private data. And sometimes an attacker could leak this system prompt via some prompt engineering techniques. And this prompt leaking is another type of attack here. And the third type of attack is somehow similar to prompt leaking. In some applications, the final prompt presented or processed by the large language model is actually a combination of the application's template prompt and the user-provided question. And a malicious user can craft the question such that it can hijack the entire logic of the final prompt to allow to manipulate the answer provided by the large language model. And this is somehow similar to SQL injection, so that's why it is called prompt injection. So this is the third type of existing attack. And now let's come back to our previous question. Is this system really safe? Actually, the answer is definitely no, because this system has the capability of executing a piece of generated code. And this piece of generated code, as discussed in the existing attacks, could be manipulated by malicious users. So this is very, very dangerous. And actually, at the time of conducting this study, some of the frameworks and applications have adopted some mitigation strategies, but none of them could prevent this type of attacks. And here are some mitigation strategies adopted by the applications and frameworks, but none of them are very suitable here. And now we know that, okay, there's such a potential attack here, and let's come to a motivating example. So PAL, or PAL, is a program-aided language model. So it is essentially, the key idea of PAL is to augment large language model with the capability of generating and executing a piece of code. And it could, the final idea is to augment the answer with the code execution result to allow this large language model to solve some problem that requires programming. And this is, as you can see, it is a very useful feature, and it is recognized by the LangChain community as useful. And they decided to implement a chain called PAL chain to allow users to generate code through large language models and execute the code. But this piece of executed code is not checked. So the content of the generated code is not checked. And this could lead to a potential attack because the user can use prompt injection techniques to manipulate the generated and executed code. And this is just an example. This is the CVE related to this chain. And what if, let's think about this question, what if this chain, because it is integrated in LangChain, it is a framework, if it is used by some application, it could lead to potential remote code execution vulnerabilities. And this type of vulnerability could sometimes give us a reverse shell, and it is very similar to web shell. So we call it LLM-shell. However, it is much more harmful than web shell in our opinion because this type of attack doesn't require a very high level of security understanding from the attacker to launch. An attacker can launch the attack by just using 1 or 2 sentences of natural language description. So that's very, very dangerous. And now I will pass on to Tom to discuss how can we detect this type of very harmful vulnerability.
And okay, after we have some background of this study, let me talk about some techniques that we used in this study. And first is how we detect these vulnerabilities. And first, we have adopted a static analysis approach to help us do this. As shown in the picture in the right, our goal is to extract such vulnerable code chain, and we can see that there is a code chain from create_CV agent, which is a user-level API, to the exec, which is a dangerous function, can execute arbitrary code, and this vulnerable chain is what we want. First, we identified a certain dangerous function at sync, such as evil, exec, and so on. And then we extract code chains on the code graph. And to improve the efficiency and the accuracy of code chain extraction, we have made some enhancement. Typically, static analysis requires analyzing the entire project directly, which can be time-consuming. And although most of static analysis tools provided the functionality of analyzing specific files provided by the user to reduce the analyze time, this is not practical in the real-world context. In the context of real-world vulnerability detection, because we cannot predict the minimum set of files involved in the code chain. And therefore, to address this issue, we proposed a new approach that can be somehow efficient. And first, we start from the code execution function async and search for the function string to identify which file may contain the caller within the code base rather than generating all the code graphs of the all files. And then we conduct a code graph analyze on these caller files preciously. And then we can figure out the caller among these code graphs, and then we can iterate through this caller by just taking them and the code list for the next round and repeat the process. And this is a backward strategy, and thus there is no need to analyze the whole project, but we can just analyze a small subset of the files. And then we can write some rules to handle the potential implicit codes to improve the accuracy of the code chain extraction. And finally, once the code chain was extracted, we manually verify the exploitability and the reachability and conduct the exploit. As a result, among 8 popular LLM integrated frameworks, we totally extracted 44 code chains and verified that 37 of them can trigger RCE vulnerabilities, and we detected 15 RCE vulnerabilities which can be triggered through user-level API, which is very potential to be used in the backend of the app, and we obtained 11 CVEs and some acknowledgement from the framework maintainer. But can we exploit this vulnerability in real-world scenarios? And to exploit the vulnerability, we should first find the potential affected apps. And for the open source apps, we can search for all repositories that use the vulnerable API on the code hosting platforms such as GitHub. And then we can extract it automatically, extracted their public deployed URLs, because as for the website, the only entrance of this website is public deployed URLs. As illustrated in the figure, we can select a risky API from all the risky API we have identified earlier. And in this example, we choose create pandas data frame agent, which can be very dangerous because it can trigger RCE, and we search for the code repository hosting platforms, and we can find many of the apps use this vulnerable API. And then we can extract some key information, such as repository name, descriptions, README files, because public deployed apps typically include their deployment URLs in these key informations, and we can extract all the URLs from these informations first, and then apply rules to filter out some noisy URLs that we doesn't need. And thereby, we can select the public deployed URLs of the app. And for the app that are closed source, we cannot access their source code directly, so we can analyze the characteristic from the collected white box affected apps, such as, for example, we find that many of the affected apps is related to data analysis, so we can summarize these categories as susceptible to vulnerabilities, and we can summarize some categories of functionalities of the app that can be potentially vulnerable. And we can collect these apps from public app markets. And after collecting these testing candidates, how to sniff and exploit the vulnerabilities hidden in the app's backend, as we cannot just judge whether the app can be exploited by just looking at it. We should test it. So to exploit these vulnerabilities while reducing the false positive and false negatives as much as possible, a systematic workflow was designed. And here is the overview of the whole process. And next, we'll explain the insight about how and why we designed these exploit strategies one by one. And the first strategy is basic usage test. And because some of it are not allowed users to input custom prompts may have broken due to lack of maintenance, and therefore attackers has no entry to trigger the RCE. So it is necessary to exclude these abnormal apps at the beginning of the whole process. Thus, we should first test whether the app can be interacted with custom prompt normally. A straightforward way is to use the prompt to let the app do some simple tasks, some simple calculations to examine whether they can fulfill our request. After the app successfully passes the basic usage test, it can be considered functionally complete, and it is ready for the normal use and interaction. However, there is a big problem that can significantly trouble the testing, the LLM hallucination problem. And during the initial phases of our research, we encountered some instances where certain apps exhibited hallucination issues, as evidenced in this figure. While we were testing this app, it generates some reasonable output. As we can see, we let it to list the all files in the current directory. It generates some seemingly correct output. However, this is due to the LLM hallucination test after we further communicate with the developers and do some code review, and we found that LLM cheated us and it generates some seemingly correct answer, but actually it has no capability to execute code. So to mitigate the potential interference caused by LLM hallucination and preliminarily confirm whether it can execute code, we designed this hallucination test. And this test is inspired from the fact that LLM cannot calculate hash functions independently. So the oracle can be, if the LLM can calculate the hash of the random string correctly, there must be a code execution behavior. And once the app passed the hallucination test, it indicates that it possesses the capability of code execution, and the code execution results are not generated by hallucination. And next, it is necessary to test whether the app can execute arbitrary code provided by us. And in this stage, we can directly confirm the existence of RCE vulnerabilities via straightforward prompt, such as we can tell it what is the final result of some malicious code or some targeted code to examine if it can fulfill our request. However, things don't always go smoothly. And during the testing, we found some straightforward prompt may fail to yield the expected RCE result. But why does this happen? And let's see an example in Pandas AI framework, because we can get some insight to, and because many of them are built upon frameworks, so we can get some insight about from why we cannot exploit the framework to get insights about why we cannot exploit the app. And in Pandas AI framework, there are two challenges while we're trying to exploit it. First one is the Pandas AI framework includes a self-made sandbox that aims to enhance security during the code execution by restricting the Python execution environment variable and filtering some suspicious keywords to prevent some malicious code. And secondly, the system prompt template in Pandas AI also significantly impacts our testing, because under this condition, our attack prompt will get embedded into this long and detailed system prompt. As we can see, this system prompt is all about generate some data analysis, data analyze code, but rather than our malicious code. And our attack semantic got obfuscated and makes it more confusing to the LLM. And as a result, LLM struggles to understand and fulfills our request. And moreover, LLM itself can have certain safety alignment mechanism. Even if we can bypass the impact of system prompt, LLM may still refuse to generate our malicious code as we desire. Thus, here comes to the RCE test with escape, which consists of LLM escape and code escape. And LLM escape aims to get rid of the system prompts of constraints or interference and break the safety and moderation mechanism within the LLM. And this enables attackers to manipulate the LLM-generated code into malicious code. And recall that previously we introduced some existing attack. Which one can be used here to achieve the goal? Yes. And they are prompt injection and jailbreak. Thus, here we use several prompt injection techniques such as ignoring instance, context manipulation, and several lightweight but effective jailbreak techniques such as prefix injection, payload splitting, and persuasion, and so on. But only LLM escape is not enough, because we just let the LLM generate malicious code we want. But there are some potential code sandbox. So code escape is to escape this potential code execution sandbox by using some tricks learned from CTF PyGel challenges, such as Python class, subclass inheritance chain, and building, reload, and some code semantic obfuscation, and so on. By combining these two techniques, we can reliably achieve RCE on Pandas AI. As shown in the diagram, using only code escape and only LLM escape cannot exploit the RCE in Pandas AI framework. And therefore, while testing the app, if RCE without escape fails, then these two escape techniques can help us get rid of the stack and bypass the potential protections as much as possible and increase the exploit success rate. And great, now we have achieved RCE on this app server, but RCE here can be categorized into limited RCE, which permits the execution of certain commands, and but not all the commands, and full RCE, which may lead to a reversed shell attack. Thus, a network access test is is conducted to evaluate the exploitability level and hazards. If the execution environment of the injected code has arbitrary external network access, the attacker can gain persistent control of the victim server via a reversed shell. Otherwise, the impact can be limited. And this attack, we can just induce the app to generate curl code to send a request to our VPS. If the VPS receives the request of the app, the network access is done. And finally, let's plant a backdoor on the app server. And the backdoor test aims to download the backdoor script from our VPS and launch a reverse shell attack. And first, we write a reverse shell script and force the app server to download it and execute it. So until now, the attacker can gain persistent control and full control of the app server. And here is a demo video about how we exploit the app automatically after the interaction of the app is automatically. And this is an open source app, and we deployed it locally, and we can see this video. And at first, the attacker should do some preparation, and such as launch HTTP servers for the POC download and open a port to listen and receive the reversed shell. And now the attacker starts to attack via prompt. And this attack has been automated. And it's opening the website. The attacker should do some preparations as the app requires, such as upload a file, enter his OpenAI API key, and so on. Now he entered his OpenAI API key and start to test. And now it's a basic usage test and a hallucination test, and so on. As we can see, the exploit is done, and the VPS received a reverse shell, and the attacker can execute arbitrary command on the app server. So this is a real-world examples. Thank you. And as a result, we totally obtained 55 suspicious testing apps. And after applying our exploitation approach, we found that 17 out of 55 are vulnerable. And even more serious, some of them are commercial apps, and some are open sourced on the GitHub, and it earns somehow 1,000 stars on the GitHub, and it is very popular. And 16 out of 17 suffer from RCE vulnerability. And 14 out of 16 can successfully exploited by reverse shell attack and gaining full control of the app server. And 4 out of 14 even can gain root privilege using simple SUID exploit. And do you think this is enough for an attacker? Absolutely no. Let's talk about what we can do after achieving RCE. After we achieve RCE, we can divide the affected objects into two categories. And first one is app host server, which can be directly controlled. And the second one is other benign app users. And this is a new attack scenario we have proposed. After achieving RCE on the app server, the attacker can silently attack other app users. Let's see how RCE can affect these two objects. An attacker attacks on the app host appears to be very straightforward. And first, attacker can obtain sensitive information on the server. And many sensitive information are stored in files or environmental variables. And for instance, many apps store their OpenAI API key in environmental variables, which can be directly obtained by the attacker, and they can steal the developer's OpenAI API key for their own usage. Additionally, for black box apps, the source code is also stored on the server, and leading to source code leakage and other sensitive information such as server kernel version, AWS private keys, SSH connection informations, and more can be able to accessed by the attacker. And secondly, attackers may achieve privilege escalation via SUID or kernel exploitation to allow them obtain more sensitive information. And last, attackers can plant backdoors on the server, as we talked previously, causing persistent control of the server and so on. Now let's have a look about how we can affect other benign app users. And basically, these attacks targeting to other users are achieved by modifying the app source code. And the first attack is user data stealing attack. And this attack allows attacker to record user sensitive data silently. And this data can be user's prompt, which may contain some IP and the user uploaded files and even user's OpenAI API key. The attacker begins with modifying the source code, and then after it modified the source code of the app, here comes to a new user, and he entered his OpenAI key to use this app, and the API key was recorded by the attacker on the server, and it can read these API keys. And the user even cannot notice their OpenAI key has been stolen. And let's see a video demo about how this attack occurred in real-world scenarios. And this is also an open source app we deployed in the local. And the app was modified by the attacker. And here comes to a new app user, and he wants to use this app. He first uploaded his files, and he wants to analyze this file. And he entered his OpenAI API key. After he entered his OpenAI API key, it got record on the server. And as we can see, the API key was recorded on the server. And the last one is phishing attack. As shown in the figure, attackers can even turn this app into a phishing app silently. And for example, the attacker wants to trick the user to download and open its malware. It modified the code first, and here comes to an app user. The modified app says every user should enter a secret token first to start use this app. And the secret token can be obtained by downloading this file. And actually, the file is crafted by the attacker, and this is malicious, and it is malware. If the user trusts the app, he will download it and try to open it. Thus, the attacker can trick the user into opening its malware. And other phishing attacks are also feasible, such as forging some website's login page to trick people into logging in with their private credential. And once the username and password are entered, they got leaked and result in some significant harm and losses. And after talking about how to exploit, let's talk about some mitigations. And for app users, for app developers, there are various potential defense mechanisms from different perspectives. And firstly, developers should focus on access control and follow the principle of least privilege, setting users' privilege to lowest possible level. And for example, they should disable the permission to read and or write the app source code and its sensitive system files or some partitions. And secondly, app developers need to ensure the environment isolation by using some proper code sandbox or some techniques to separate the code execution environment from the app server's running environment as much as possible. To achieve this goal, some sandbox like process level sandboxes like PyPy sandbox lib, some cloud sandbox such as E2B, or some tools like Pyodide that embedded the code execution in the browser using some Node.js and Wasm technique, allowing the code execution to run on the client side rather than the server side to prevent the code execution on the server. And in addition, prompt level defenses can also help for somehow to filter out some prompts with malicious intent. And here come to our conclusion of this talk. And in this talk, we systematically introduce a new attack surface in LLM system, which can lead to RCE, and we call this LLM4Shell, LLM shell, and because it's similar to web shell, but in some situation it is powerful more powerful than the web shell, because the attacker can achieve RCE by just using 1 line or 2 line natural languages. Also, we talked about the exploitation in the real world scenarios and designed the exploitation workflow. And finally, we provided some potential mitigations for the developers to protect their products from different perspectives. And in one word, please be aware of your LLM-integrated frameworks and apps. Protect them as possible as you can, because maybe one day the attacker can achieve RCE on your app server just using 1 line or 2 line natural languages. And thanks for your listening. And this is our reference. And thanks.